So it's a big morning. Today's question is called Validate Binary Search Tree. Well, we are given a binary tree. Determine if it is a valid binary search tree, a BST. And a valid binary search tree is defined as follows. The left subtree of a node contains nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both left and right subtree also be binary search trees. Excuse me, I drink cold water in the morning, so I'll be like this. Excuse me. And here is an example. So the subtree, every node from the left child will be less than this node, and all the nodes from the right subtree will be greater than the node value of this node. And here we can actually, the first thought might be we can compare our child node to our parent node to check if it is a valid binary tree. But you see, the left child is less than 5, and yes, here the condition is valid. And here, the right child is less than, it's not greater than the current value, so it's not a binary search tree. All right, let's write some our own examples, like 5, 3, 8, and if we just use the parent to compare, we will have some situation like we'll have some condition like this. You see, you compare the left child node to the parent node, and yes, it's less than the parent, and here grade 8 is greater than 5, and that's okay. And we check 4 is less than 8, yeah, and 10 is greater than 8. Then we'll say this is a binary search tree. But actually it's not, because you see the node 4 here is actually less than the node and the root node. So the condition doesn't hold, because there are some node in the right subtree that is less than the root node. So that makes this not a binary search tree. So how do we compare this node to this node? Actually, we will need some information. For each node, we will need some information from its ancestors, right? Like, what is the valid range for this node? It has no information, right? So we have to have some way to pass this information from the parents, from ancestor of this node to this node. Okay, so one condition is that this, let's say we are talking about this node should be greater than like 5. So there will be a lower bound, and this should be less than basically everything. Like it will be positive infinite number, because we can have this like this, and this still a valid binary search tree. Okay, so what about this? What about, okay, so case 3, we must less than, let's say, negative infinite, because we can have a very small number like this, and that doesn't matter because we just have to be greater than the left child. But it cannot be greater than, it should be like this, and it cannot be less than, it should be less than the upper bound. Okay, because if it is greater than 5, then this will not be a binary search tree. Okay, and how we're gonna do this? Well, oops. All right. Let me turn on the AC. It's a little bit hot here. So we start from here. We check if this node is if this node is greater than its lower bound and less than its upper bound. And if we initialize, let's say we only have one node, and what will be the lower bound and upper bound? The lower bound will be negative infinite, and the upper bound will be positive infinite. Alright, so in this case, we don't have to check anything. Yes, we have to check. We have to check one is greater than the lower bound and less than the upper bound, and that's it. And what if we have this simple case? And again, do we have negative number? Yes, we can have a very small number. Alright. Or we can use the node as its upper bound and lower bound. So in here, lower bound will be null because we just start, and upper bound will be null, and there's nothing to compare. We will just return true. And what if we are having this? At the beginning, we have lower bound and upper bound both null, and when we recurse on the left, what upper bound do we have? The upper bound will become 1, and what lower bound will become, and it will still be null because there's no lower bound for this left child. So we check if 0 is less than the upper bound, and it is, so it's a valid, and we can just return that. And when we recurse on the right child, what will be the upper bound? It's basically nothing, right? The upper bound could be anything greater than 2, but the lower bound will be greater than 1, so the lower bound will be 1, and it is greater than 1, so we return. Okay, and what if we had something, let's say we have something like this. When we recurse on this node, what will be the, what will be the upper bound and the lower bound? The lower bound will still be 1, but we have the upper bound right now, because to this to be a binary search, a valid one, 2 cannot be greater than 3, so the upper bound will be 3. Alright, and they are no equal. It's not less than or equal to. It's not greater than or equal to. It's just the less than and greater than. Right? And yes, it meets the requirements. And for 4, the lower bound is 1 and the upper bound is null. Okay. So basically, we're just gonna maintaining a lower bound and upper bound, or a lower node or upper node. So for each node, we compare it to both the upper bound and the lower bound, and we check if it meets the requirements. Alright? And doing this, we will have to go through each node. We're gonna visit every node in the tree. So the time complexity will be O of n, because there's nothing. Although this is a binary search tree, we cannot skip any nodes. You know, we cannot skip checking any node. And the space complexity will be O of h, where h is the height of the binary tree, and we can use log n, basically the same. Alright. So if that sounds good, let's jump right into the code. Let's code it up. Okay, so first we were gonna have a struct for our tree node, and let's just use an integer. And the left, we have another pointer to the right, and we'll just make a simple constructor. Okay, and our function will return a Boolean value, so it will be a return type, and also it will name it is valid bst. Okay, so you will take in a tree as the input, call it root. Okay, and we know we are gonna maintaining an upper bound and lower bound. So we're gonna have another helper function, and we'll have a lower tree node. Another is it will be the upper. Okay. So here we can just call this function with our root, and the lower and upper we'll just make it a null pointer, because for the first node there's nothing to compare. It could be anything. Okay. So first, our base case, when the root is in, when this is a empty tree, let's say what will happen. Oh, we can have an empty tree, but when we do our recursion, we will get an empty tree, and what we're gonna return, we are gonna return true. All right. Okay, so let's say we have a root node. We will compare to the left, compare to lower, compare to upper. Okay, so first, if we have to check if the lower is a node pointer, it's a node value, it's a node. If it is, we can just skip the comparison. But if it is not, then we will have to compare. So if it is not a no node, then we will compare our root. It should be greater than our lower. And actually here we are gonna check if it's less than lower, we will return false. Just let's make an example of that. Let's say we have 5, 5 and 4, and here for this node that the lower bound is 5, but 4 is less than the lower bound, so we're gonna return false in this case. Alright. So here we actually do the opposite. Root value is greater than the upper, and we return false. Okay, so after we've done this and we did not go in each of these are not returned, don't each of them did not, each of them doesn't return false. So if we pass these two conditions, then we hit here. So it is the time that we know our current root node is a valid binary search tree node. So we can continue on our left subtree and the right subtree. So we can just call this function root on the left, and these will be upper bound and lower bound. And also another one, root on the right. We have to use AND operator here because for a tree to be a binary search tree, for a node to be a binary search tree node, the valid one, both its left and right child should also be a valid binary search tree. So for the left subtree, what would be the lower bound? It will still be the current lower bound, but the upper bound, it will be upper bound will be the current root node, and for the right subtree, the lower bound will be the current root node, and upper bound will still be the upper bound. Okay. So I think let me run through an example to see if we got this right. Okay. Let's remove this. This is obvious. Okay. Alright. This is our example. And first, upper and lower. So first, this is our input root, and it's not a node, so we compare it to the left and right, but both of them are a node pointer. So it will just skip this to check, and we will recurse on the left and right with the lower bound still be null, and the root will be the upper bound, which will be like this. So here, now we have another run of this function with the input 0, and it's not no node, and we compare the lower, and we will skip that because there's no lower bound for this node. And here we have an upper bound, so we check if its value is greater than the upper bound, and it's not, so we pass this test and we keep recurse on the left and right, but its left and right is actually a no node, so we should just return true. Okay, so we will go back to here and keep recurse on the right. So on the right, the lower will be 1 and the upper will still be null. Okay, so for 3 is greater than 1, so it will not go into here. Okay, we pass this, and we have no upper bound, so we also pass this, and we keep going on its left and right child. So for this, for the left, the lower bound will be will still be 1, and the upper bound will be root, which will be 3. So here for this node, it has to be between the lower bound and upper bound, and it is, so you will keep recurse on the left and right, and will return true because there are no nodes. And we go back here and we do the right child, and for the right child, the upper bound is still be null, but the lower bound becomes 3, and in this it meets the requirement, so it will return true for this, and it will return true for this. So in the end, we will get this binary tree is a valid binary search tree. Okay, so that is our example run, and let's write some test case for this regular example. Tree node root. Let's use the example like we can use this. Okay, so the root node is 5, and it's left 1, 2, 3, 4, 5, and it's right, and this left is right, right, left, and right, right. So 5, 1, 4, 3, 6. Okay, so let's call our function here and passing the root, and we expect it to be a true. Yep. Oops, we expect it to be a false because this is not a binary search tree. Here, this should be greater than 5. And another example, false. Invalid BST. I think this would be a better name. Valid BST1. And here are only 3 nodes, 2, 1, 3, and we expect it to be true. And we also have to test for single node tree. This will be the base case. Empty tree. So for empty tree, it will be like a no pointer, and we return true for it. And for a single node tree, this also should be a valid binary search tree. Okay, so let's run our test case. Oh great, we forgot a semicolon here, and that's good. We passed all the test case we created. And I think it is time for us to copy and paste the code to LeetCode to check if we can pass all the test cases on LeetCode. Alright? We will have a function, helper function here. Let's make some more space. Alright, and we will return it like this. Let's run the code. True. Then submit it. Wrong. What happened? What happened? We can pass the input 222. Alright, let's try if we have a 222, and it should be an invalid. Let's make it here 222. Should be a false, and we run it. We should get one test example of false. Yes. So what happened when we have 2 2 2? In this case, we'll return true. Why? Well, because we cannot be equal. This 2 should be strictly less than 2. If it is equal, then we will return false. So here we have to add that. Okay, so let's run it again. Oh, cool. Alright. Let's try it again. Here. I found you. Let's submit that again. And great. We have that passed. Alright? Be careful for this little tiny equal sign. Okay. This is so critical. Alright. I think that's pretty much it for this question.